Hello and welcome to this lecture. We are going to talk about physical vapor deposition, and in physical vapor deposition we are talking about sputtering. So, we already have seen in previous lecture about thermal evaporation and electron beam evaporation. So, let us see what exactly sputtering is and how sputtering is different than thermal and e-beam evaporation. Now, in both thermal and e-beam we have seen that we are applying a thermal energy either by applying a voltage to a boat or a coil, and that source holder, what we call boat or coil, will get heated up and the material which is loaded onto it will get melt and then it will start depositing, evaporating and depositing, right. In case of e-beam also we were doing similar things, but instead of applying voltage to the crucible that was holding the material, we were using electron beam, right, that is generated through the filament, and that filament electron beam will get accelerated through accelerating electrodes. It can bend using magnetic field about 270-degree arc, and then we can use extra magnetic coils to sweep it onto the crucible, that means onto the material loaded on the crucible, and that material will get melt and it will be evaporated. So, in both the cases we are thermally depositing a material onto the substrate. In sputtering it is little bit different. In sputtering what we do is rather than melting, we are going to dislodge the atoms from the source, and that atoms would get deposited onto the substrate. So, let us see this sputtering. If you see the slide, we are going to talk about sputtering, and in sputtering there are 4 different categories: DC sputtering, RF sputtering, magnetron sputtering and reactive sputtering. In this case, instead of we using the targets like chunks, we are going to use targets which looks like a disc, toroid, plates, etc., and different sizes as well. As an energetic ion strikes the surface of the material, there are 4 possibilities. So, what happens is in a sputtering chamber you have substrate, you have a source, and here there is a plate. Let us say this is the substrate, okay, and this one is the source, or in this case we call this as a target, and then we have argon gas, and we give anode and cathode to the substrate, and the so we give a bias. So, when you do that high DC sputtering or RS sputtering, then what will happen is the formation of plasma. When there is formation of plasma, this argon gas, which we say that high energetic ion strikes, this ion strikes this particular target or source material, and it will dislodge the atoms from this one, dislodge the atoms, and those atoms will start forming a film onto the substrate. Okay. Again, so an energetic ion strikes the surface of the material, there are 4 possibilities. One, so this is exactly the process for the sputtering, but what should be the how much should be the energy of the ions so that the sputtering occurs and not other things. So, what are other things? So, one is ions with very low energies may simply bounce off the surface. At low energy the ion can be adsorbed on the surface. At about high energy 10 kilo electron volts, the ion penetrates in the material and many atomic layer spacing, forming ion implantation, right. Ion implantation or diffusion for the MOSFET, you know, if we want to create source and drain, right, and of course there is a thin layer of oxide which is we call a gate oxide, on which you have a gate, right. This N plus or P plus, depending on what kind of MOSFET you want to fabricate, right, you have to use diffusion technique or ion implantation technique. So, when the energy of the ions are very high, then what will happen is you can instead of dislodging atoms, ions will get implanted into the substrate, and that is what we call as an ion implantation. Thus, the energy of the ion hitting the source is very important. So, between these 2 ranges, both energy transfer mechanism occur, and substrate atoms or cluster of atoms will be ejected from the surface of substrate, and the energy should be somewhere between 10 to 50 electron volts for a right kind of sputtering to happen. This additional energy provides sputter atoms with additional surface mobility for improved set coverage relative to evaporation. Now, let us go to next slide. Now, when we have to also understand that what is the yield of a particular technique. So, for the yield, sputtering yield is given by the number of sputter atoms to number of incident ions. How many ions are hitting the source material or the target material and how many atoms are dislodged from the target material, so that it gets deposited onto the substrate. That is the yield of the sputtering. Sputtering yield also depends on several things. For example, the binding energy of the material, then it is also dependent on the proportional square root of energy of ions, proportional to the ion and target atomic mass, proportional to the angle of incidence and reduction in deposition pressure. These are some of the things that is sputtering yield is dependent on. If you see these three different images, the first image shows that how the ion energy affects the sputtering yield. Second one is shows, which is here, let us say this is 1, this is 2 and this is 3. So, we have second shows that how the angle of incidence will affect the sputtering yield, and third shows that how the pressure of the system will affect the sputtering yield. So, as you can see here, right, the binding energy and sputtering yield inverse proportional. Energy of ions and sputtering yield square root of, so sputtering yield is proportional to square root of energy. If atomic mass, directly proportional. Proportional to angle of incidence, rate is proportional to angle of incidence, right. So, these are all the parameters that we have to take care when we are going to use sputtering system. Now, let us come to the first sputtering, which is DC sputtering. As I told you, there can be anode, there can be cathode. We can put the target region on the top or target region on the bottom. That means that you can have source or target here and substrate here. This is substrate and this is target. We can do that also, or the one that is shown in this figure, right. As usual, what we have seen in the thermal or e-beam operation, where your source always was at the bottom and the substrate always was at the top. But in this case, we can interchange it. We will only take care of the potential that we apply. That means which should be the anode and which should be the cathode. The anode is generally the substrate and the cathode is generally the target or the source material. So, as you can see in this particular image, the substrate is attached to the anode, the cathode which is the target material is loaded, and then what happens is this is loaded on the plate, and there is a water cooling, because again the argon ions that comes, argon gas comes here, right. Because of the anode and cathode high voltage between these two plates, the argon gas there will be a generation of ions, and those high energetic ions will heat the cathode and which dislodge the atoms, and those atoms travels to the substrate and gets deposited to form a film. So, at low pressure the cathode sheet is wide and ions are produced far from the target. Mean free path of detached atom is given by lambda is inversely proportional to the pressure. As the pressure is increased, the fixed voltage, the mean free path is decreased, more ions are generated. But the pressure is too high, the sputtered atoms undergo increased collision, scattering and not efficiently deposited. So, again very important thing is the pressure of the chamber. We can see in this particular slide how the argon pressure affects the overall properties in terms of sputtering yield and relative deposition rate, and at this particular condition, which is typical sputtering condition, you will see what should be the pressure and what should be the current values. The optimum condition is shaded in the graph, which I have just shown here in this particular slide, in this particular image, right. And this range of pressure is suitable for the DC sputtering. In general, the deposition rate is proportional to the power consumed and inversely dependent on the electrode spacing. So, another thing also you to understand that if you increase the spacing between the source and the substrate, right, the rate of deposition also affects. Closer the things, faster the deposition, farther the things, difficult in terms of getting the higher deposition rate. But there are advantages, disadvantages when you have a spacing of certain distance. This affects the overall film property, that means spacing between source and target. Okay. So, the RS sputtering, now we go from DC to RS sputtering. Here we are using 13.5 megahertz as a RF frequency, right. So, this one in this particular case, you can see the chamber remains as it is. There is a substrate, there is a target. Now, you see here, right, what happens is the target is on the top and the substrate is at the bottom, right. I told you it can be either or, right, and then we can have a heater, right. So, this is a substrate on a plate, this is a target or source, right, and the reason of having this planar heater is to improve the crystalline property of the film while the atoms are depositing. It can rearrange itself. You remember in thermal evaporation it was very fast rate of deposition, that is why the atoms would have very little time to rearrange itself. Here the we can use the heating to rearrange the atoms, and that particularly this kind of heating will affect the overall film properties for better. For example, if you want to grow a piezoelectric film, heating of the film during deposition will give us a better orientation of the film. Now if you see this particular image, what we have is RF frequency. So, RF power supply, and we are giving this between the two plates. There is a pressure control system for the input gas, which is our argon. Then we have vacuum pumps, we have temperature control system, there is a vacuum control system, and what happens is that the RF films, RF sputtering in particular is useful when we want to deposit insulating films, which is having very high resistivity, about 10 to power 6 ohm centimeter. Now generally I am sure that you know what is resistivity, but lot of time student gets confused. So we can say R equals to rho L by A, so that gives rho equals to R A by L, and when you put the things like resistance is ohm, this is ohm, centimeter square, and by centimeter, so this becomes ohm centimeter. That is a resistivity unit. Okay, unit of resistivity is this one. So that is how resistivity of 10 to power 6 ohm centimeter comes. At AC signal about 50 kilohertz, electrons oscillating in the glow, electron oscillating in this particular glow, which is plasma, acquire enough energy to cause ionizing collisions, reducing the need for secondary electrons. Secondly, RF voltages can be coupled through any kind of impedance, so electrons need not to be conductor. This is very important point, that in the case of DC we said anode and cathode both should be conductive. In case of RF we not need to do that, because as you know RF voltages can be coupled through any kind of impedance. So it is possible to sputter any material irrespective of its resistivity. Typically RF frequency is, as I said, 13.56 megahertz. This is as per the Federal Communications Commission. In RF sputtering, the target cell biases to negative potential and positive ion bombards sputters away the atoms for subsequent deposition. As the target is capacitively coupled to RF generator, metals as well as insulators can be deposited. So we can use RF sputtering for depositing metal, insulator, and of course we can go for semiconductors. Okay. Now let us understand what is the use of magnetron sputtering. Now whenever you use any magnet and effect of magnetic field along with this sputtering, it may be DC sputtering or RF sputtering, we call it as a magnetron sputtering. So it can be DC magnetron sputtering, it can be RF magnetron sputtering, and so on and so forth. So in this particular case, as you see, there is an anode and cathode, which is in A, and then again you have the same thing in B and C. Now let us see how the magnetic field, when it is in parallel to electric field, or how it should be, so that we have a better rate of deposition. So in magnetron sputtering, a magnetic field of strength B is superimposed on electric field E between the target and the substrate. So when we know that the electron within the dual field environment experiences the Lorentz force, which is given by F equals to m dV by dt equals to this particular equation, you can see very easily. So E plus V into B, where Q, M and U are the electron charge, mass and velocity respectively. First consider the case, let us consider case where the magnetic field and electric field are parallel, as shown in figure A here. When the electrons are emitted exactly normal to the target surface and parallel to both the fields, what happens is this V into B becomes 0, and only what is left is the E, which is the electrons. So electrons are only influenced by the electric field, which is E. So electric field, when I say only what is left is E, that is the field, electric field, which will influence the electrons. So there is no effect of B here when B and E are parallel. Second case, let us consider case B here. In this case, what will happen when the electric field is neglected, there is no electric field, only magnetic field you apply as shown in B. What happens is electron is launched from the cathode with velocity v at angle theta with respect to B. It experiences a force q v b sin theta in a direction perpendicular to the B. The electron now orbits in a circular motion with a radius r that is determined by balance of centrifugal force and Lorentz forces. The electron motion is helical with constant velocity v cos theta. But this is not really what happens if there is no magnetic field, right? If magnetic field were not present, such off axis electrons would tend to migrate of the discharge and lost at the walls. So, the effect of magnetic field is shown when we are using magnetic field without having presence of electric field. But if you have electric field, then what will happen is that the motion of electron is helical with constant radius, but because of electron acceleration in electric field, the pitch of helix lengthens with time. Time varying electric field helps in varying radius of spiral path. So, when we have magnetic field and electric field, what will happen is that and that too particularly the effect of magnetic field is to help the or increase the rate of deposition, because what happens is magnetic field will prolong the electron residence time in the plasma. If the electron residence time in this particular plasma is higher, then what will happen, more ions will hit the target and more number of atoms can be dislodged and get deposited onto the anode. So, this residence time increases only because of the magnetic field, and if the magnetic field is present, then we can change the length of the helix by changing the electric field. Okay. So, that is the advantage of having magnetic field along with electric field. Applied magnetic fields have the desirable effect of reducing electron bombardment of substrates and extending the operating vacuum range. This is the same image where you have magnets, the negatively charged electrode, there is a substrate, and because of the presence of magnet, the helix that is formed can lengthen one, and the residence time of the electron in the plasma increases. Okay. So, that is the advantage of the magnetron sputtering. Then we have something called reactive sputtering, in which the thin films of compounds are deposited onto substrate by sputtering using metallic targets in presence of reactive gas molecules. This is only for your information, right. When we have the videos for you where you exactly see that how we are using the magnetron sputtering. Okay. But people also use reactive sputtering, and particularly when we have to deposit oxides, nitrides, carbides, sulfides. So, irrespective of which of this material considered during reactive sputtering, the resulting film is either solid solution of alloy of the target metal doped with the reactive element, a compound, or some mixture of two. So, that is the advantage of reactive sputtering when we have to go for multiple materials. We also use bias in all the sputtering, and in the bias sputtering what happens is the electric field near substrate are modified in order to vary the flux and energy of incidence charge species, and achieved by applying either a negative DC or RF bias to the substrate. Target voltage is generally by between -1000 to -3000 volts, but the bias voltage is generally between -50 to -300 volts. Due to the charge exchange process in anode dark space, very few discharge ions strikes the substrate with full bias. Now, if you really want to understand the anode dark space, Crook dark space, that comes under the thin film physics kind of lectures, which is not part of this particular course. That is why I am not going into detail about the anode dark space and what other things are present when there is a plasma. Between plasma and anode and cathode, there is a dark space between that, and how these electrons would travel through this one, right. That is a different phenomenon. Okay. So, let us not worry about it, but let us come back to here. The technique has been utilized, which one? Bias sputtering in all DC, RF, magnetron and reactive sputtering to alter broad range of property in the depositor films. Now, the advantage of bias sputtering is that we can tune the resistivity, stress, direct properties, optical properties, H rate, and addition of the deposited films. This is how the sputter deposition works. As I told you, there is a target, and then there are wafers or substrate. These wafers are on the electrode, which is anode. There is a heater to improve the crystal orientation. There is generation of plasma, right. There is a vacuum. The sputter gas is argon, and we apply a voltage. In case of DC, it is a plus minus, so anode and cathode. Plasma is needed to make the gas conductive, and generated ions can then be accelerated to strike the target. High pressures and evaporation about 1 to 100 millitorr, better at deposition of alloys and compounds than evaporation. So, if there is a alloy, we have discussed this thing also in the E-beam and thermal, that depositing alloy is becoming difficult. It is very difficult in case of thermal or E-beam. In case of sputtering, using reactive sputtering, we can do that comparatively easily. This is a better image in which you can actually see that how argon ions are hitting the target material, and how the atoms are dislodged and starts depositing onto the substrate or a wafer. So, other things remains as it is, like there is a vacuum, so high pressure, low pressure, and then we have to go for Pirani gauge, panning gauge, there is a substrate heater, there is a rotation of the substrate, everything is as it is. This is how the system looks like, sputtering system looks like. Okay. This also comes in vacuum evaporation because we are creating a vacuum, and in a at a glance, if you want to understand this sputtering, of course, this is a viewing window, this is a chamber, these are all the the vacuum pump, all the gauges, everything, and that this is a control electronics, your control system. Right. So, plasma is generated by applying RF signal producing energetic ions. Target is bombarded by these ions, ion knocks atoms from the target, sputtered atoms are transferred to the substrate. Wide variety of material can be deposited because material is put in vapor phase by mechanical rather than chemical or thermal process. Here we are not heating and melting it, that is why we can deposit different kind of materials. It can be used for excellent step coverage, sharp topologies because of higher chamber pressure. If you remember, the limitation of the thermal and E-beam was that the step coverage was not great. Finally, film stress can be controlled to some degree by chamber pressure and RF power. The advantages and disadvantages of sputtering are following. Advantages are it can we can deposit film on large size targets. Then we have film thicknesses can be easily controlled by fixing several parameters, pressure, operating parameters such as deposition and adjusting the deposition time. We can control we can use sputtering for depositing alloy. The step coverage is better. The sputter cleaning of substrate in vacuum is possible, and in the E-beam evaporation there can be a generation of secondary X-rays, right, which X-rays are generated because of the electron beam hitting the target. There can be generation of X-ray, but in case of sputtering there is no generation of X-ray, and that is why there is no device damage. The disadvantages or limitations of sputtering are it is first is high capital expenses, second rate of deposition of some materials such as SiO2, which is an insulating material, is low. Some materials such as organic solids are easily degraded, and greater probability to introduce impurity substrate because of the because this particular former operates under a high pressure. In general, we will see the chemical vapor deposition, but if you compare the physical versus chemical vapor deposition, compare the physical versus chemical vapor deposition, then what happens is the advantages of PVDs are that high rate of deposition compared to chemical vapor deposition. There are no harmful exhaust gas, but the limitations are uniformity is not as good as CVD, and step coverage is poor compared to CVD, because in CVD when we will take CVD lectures, you will see that the gas will react, the chemical gas reactant will react with all the parts of the substrate, and that is why the step coverage is way better. If you want to compare evaporation, which is thermal and E-beam with respect to sputtering, then there are several parameters: rate, choice of material, purity, substrate heating, surface damage, in situ cleaning is possible or not, is there a damage by X-ray or not, decomposition of material is possible or not, uniformity, capital equipment, number of deposition, thickness control, adhesion, shadowing effect, film properties like grain, size and step coverage, everything we can compare, and we can select which process or which technique we can use for particular film that we are interested in depositing. So, in summary, if you want to just understand about physical vapor deposition, then it is a technique based on formation of vapor of the material to be deposited onto a film. The material is in solid form, is either heated until evaporation or sputtered by ions. In sputtering, ions are generated by plasma discharge, usually with the inert gas, which is mostly argon. It is also possible to bombard the sample with an ion beam from external ion source. This allows to vary the energy and intensity of ions reaching the target. Okay. So, that is all about this sputtering, and I will take another class on micro machining, where we will see how we can use the surface and bulk micro machining to create diaphragms. So, till then look into this particular lecture, sputtering. The speed at which I have recorded this lecture was deliberate, because now you should understand how thermal evaporation and E-beam evaporation works and how the vacuum deposition works. So, it is more like understanding the technique of depositing, right. So, let us meet in the next class with a new topic. Till then, you take care. Bye for now.